Yes. So I'll go on. So sorry, I'm Satya Katla. I'm working as a staff systems engineer at MBS Space, where I work on the 5G NT and related stuff. But I would like to take this platform as an opportunity to talk something that is very different from what we are currently looking at in this panel. And even I want to discuss something which is not often discussed in the mainstream debates or discussions in the machine learning or AI platforms. So before I begin, I would like to say that the views presented here are my own and it's not in any shape or form associated with the organization I'm affiliated with. Okay. Whether can you see my video, by the way? Or is it okay? Yeah.
Yes.
Sorry. So basically, the machine learning, the AI ML, how does it work? It works under the AI ML. The framework is a probability theory. It's a mathematical framework of probability theory. Every task, you name ChatGPT or predicting stock prices or image classification or weather forecasting or anything. It's a statistics that's underlying the models basically, and every task of this involves probability. But how are these probabilities defined? And for example, ChatGPT, how does it work? So we have a neural network layer, and then there is a probability distribution, which will compute it based on the previous training data, and then it forms. The probabilities are taken based on the training, and then meaning is made out using chat. Based on the context. So ChatGPT predicts the next word by choosing the one with the highest probability. And similarly, spam filtering, based on the training data, you compute the probabilities that email is spam or not. So a medical diagnosis, which is dangerous, I would say. I mean, they use probability, of symptoms that match a certain conditions, and then they say, oh, there's a tumor or there's a cancer or something. I'll tell you. I'll explain why this is a bit dangerous. And then image classification, yeah, as we know, this machine learning has originated mainly from the image processing. So they compute the output probabilities for each class, then choose the one which is most likely the case. For example, cat, dog, etc. So this is how the basic works. So underlying principle is the probability. So without probability, there is no statistics, there is no machine learning or AI. So, but what is the probability? So the probability is, everybody who is in wireless comms background or electrical engineers, they know that it is the ratio of favorable outcomes to the total number of possible outcomes. And there are two schools of thought, primarily frequentist probability based school, and then there's a Bayesian probability based school. So in fact, frequentist, basically it is the defined probability is a measure of frequencies. So how often you observe the patterns or the data, over a repeated set of measurements. And Bayesian school is defines probability as a measure of belief. So they have, they say that we have previous data, and then you make an assumption on some of the parameters that generate this data, and then you define the probability on that. But however, both either frequentist school or Bayesian school, they both rely on having a meaningful probabilities. That means, there is a probability defined. The probability is basically the number of favorable outcomes by total number of outcomes. But what do I mean when I say a meaningful probability? So there is no probability without ergodicity. This is often missed in machine learning or AI, mainstream discussions, or rarely taught in computer science and electrical engineering departments. So there's no, everybody talks about probability, but actually probability exists only if there is ergodicity. What I mean by ergodicity is that, so if you coin the toss, over 100 times, and 100 people coin the toss, at the same time, then if the both probability match, and one person tossing the coin 100 times and 100 people uh, tossing the coin, where the both probabilities match, like probability that's head or probability of tail, then it is ergodic, and then the probability exists because there's a probability in space is equal to probability in time. But however, if you look, yeah, this is ergodic, by the way. So if there is if you're playing a Russian roulette, and you have 6 bullets in the pistol or a gun, and you play alone, then what's the probability that you'll survive? If you play 6 times, then you're going to be dead. You have no more, you're ruined basically. And but however, if you 6 people they play in spatially, then the probability that you will survive is 1/6. So that means the both probabilities not match. So one is in space and one is time. Only when they match, then the probability has some meaning, and then you can define probabilities, and you can do statistics, you can do machine learning, everything. But how often do we encounter this probability with ergodicity, ergodic behavior? So the most of the assumptions that are vital in the machine learning is the Gaussian, the CLT is central limit theorem, which I'll discuss a bit later. So they assume the Gaussian assumptions are fundamental. The Gaussian assumptions are fundamental to many statistical inferences processed in machine learning and data science. However, in reality, we do not see normal or Gaussian distribution. This is widely abused distribution, and what we see most often is a non-ergodic behavior, which arises due to fat tails. What we see when I mean fat tail, so if you look at the this peak here, can I point? So this one is, you have a peak here with more occurrences, and then this here it narrows down, and then you'll see a fat tail. This is basically you have more observations here, which confirms that your theory is right. But then you have a tail here at the very 10 sigma or 20 sigma, you still have a probability here. But whereas a Gaussian, you will this peter out the there is thin tails. These are called thin tails because there's no probability, and they'll have fatness here, but then they will fall down rapidly. They'll decay rapidly. So this is a Gaussian distribution, whereas the first one, this peak, you have a more and more observations. So that means, like, if you see a more and more swans which are white in color, you'll think that all swans are white. But then one black swan will ruin your years of corroboration. So this is what the fat tails is. So most of the real world happens here in the fat tails. So for example, if you so when do I, or how do I know that the Gaussian is assumption is wrong? So when do I use the Gaussian as an approximation or assumption in my machine learning? So if you look at this, if when somebody says that there is an event happened, extreme event, there is a COVID, or there is an Ebola outbreak, or there is some financial stock market crash. So when they say that event happened, then the probability that your model the assumption that you have taken, it is a Gaussian, given that this event has occurred, will be very, very small. So if you see here, so we have considered the event to be power law or fat tail distribution, and we say that's a 10 sigma event. Then what is the probability that that will be Gaussian? So you can never assume it is a Gaussian unless that probably the event has happened. Unless it is one, you can never assume that it is a Gaussian. That means only God has to tell you that there is a that it is a the data is, or the event is coming from a Gaussian distribution, and it's a 10 sigma event, which means very, very likely to observe. But if it's not a 10 sigma event, and if it's coming from a power law or fat tail, so it is not that it is a 10 sigma event, but it is coming from a fat tail. So fat tails, so perils of fat tails. So why machine learning fails in this case is because the central limit theorem, CLT, which I was discussing, it works very, very slowly because because of the fat tails. You need lots and more observations, and even if it works at asymptotes, but doesn't say anything for pre-asymptotes, because we have finite amount of data, and it converges very slowly, the CLT. So CLT says that we take average of random variables, it converges to Gaussian distribution, but it doesn't converge quickly for fat tails. So you need to have a large number of data samples. So, but we have only finite number of samples, and this is only for finite mean and variance fat tails. If most of the fat tails or heavy tails, they do not have a finite mean or variance. So in that case, the CLT breaks down completely. And I often see that people accusing, I mean, people saying correlation is not causation. The the economists and social science department, they come up with weird correlation and say, eating egg causes cancer, eating egg causes increases diabetes, red meat causes cancer. So these are rubbish, because they forget that correlation is not causation. It is correlation is not correlation, because when you look at the factors, when the data is, because there are many factors that affects the behavior, and when you take random samples from a factile and you correlate it, you will keep changing. You will not get it. It's not converges. It will not converge. For example, if you see here 2,000 samples, I get some number here, and 10,000 samples, I get number. It's all different samples. You see, there are different correlation values for the same set of data. So it doesn't converge. No matter how many samples you take, you will get, one time 0.1, one time 1. You will get high correlation, low correlation. It's always bounded between 0 and 1. So I mean, minus and 1 and 1, but it doesn't converge. So for example, if you look at y is equal to x, so
Yeah, your time is over, Satya.
Yeah, just finishing here. So when y is x, the correlation is 1, and when y is equal to x square, correlation is 0, because the correlation works only for the linear things. It doesn't work for the non-linear things. So conventional statistics fail under factors, and you should not use unless you know that this is a thin tail distribution, or the data is not coming from factor. And you have to look at the law of medium numbers, not the law of large numbers, which is the case in factors. So anyway, some questions that we need to look at while designing a machine learning is that how much more data is needed, how does the pre-asymptotes look, and what is the speed of convergence. So here are some references if you're interested, and if you want to learn more about this, and if you are intrigued by this topic, which is not from 5G NTN, but if you think it is something interesting, then I'm happy to discuss. Please contact me on this, my email or web space. Thanks very much, Kamesh. And